Hi guys, welcome to the vodcast on the tech-able part of SAC2. Strap yourselves in and enjoy. Okay, question one, multi-choice, was your token kinematics question. It really relied on the very simple understanding that velocity is your rate of change of displacement with respect to time. And if you had to work out its position at a particular time, you could use the definite integral approach, given that you know at t equals 0, it's at position positive 2. Okay, so there it is. We had to work out its position at t equals 5, and there's the use of the definite integral to achieve that means. Okay, moving on to the second one, you had to work out an expression for the antiderivative of that rational fraction. Rational fraction, immediately you should be thinking about partial fractions, and so what you can see there is the attempt to express the given rational fraction as a sum of partial fractions. There was no need to pull out some long-winded algebra when you could simply whack it into your CAS under expand. If you use the interactive, it gives you the prompt partial fractions, and when the output appears as so, and then it's a case of identifying, well, which of the options there matches the given one, and it turned out to be the first one with just the two numerator components split into two different fractions. All right, this was a test of your understanding of integration by recognition. So you're given a rule for the derivative of the square root of x inverse sine the square root of x. So what do you do with integration by recognition? Well, you think of just taking the integral of all of that, inverse sine square root of x all over 2 square root of x plus 1 over 2 square root of x minus 1 dx is equal to your starting point, square root of x inverse sine. That's how you'd begin the thought process. You wouldn't need to write this down. And then it's a case of, well, you've just got to use your properties of the definite integral to isolate that dx. So you needed to separate the two. So in fact, so it's half inverse sine square root of x over square root of x dx is equal to square root of x inverse sine x sine square root of x minus 1/2 of the integral of 1 on square root of 1 minus x dx, which we could actually work out. And ultimately, to work out the required integral, we just need to multiply everything through by 2, and B was your answer. Okay, question 4, we're presented with a graph of y equals cos cubed pi x. And it's clearly an area below the x-axis, so it, of course, immediately you should be thinking has negative signed area. So to work out the area, we need to take the definite integral between the two x-intercepts, which are pretty easy to determine, 3 on 2 and 1/2, and multiply the definite integral by -1 to get a determination of area. Okay, the rest of it, of course, is a test of your ability to go through the routine of cos or sine to an odd power. What does that involve? That involves the Pythagorean identity. So we write it as cos pi x 1 minus sine squared pi x. We let u, okay, we get a change of variable going, u equals sine pi x, leading to, missing a bracket there, du dx is equal to this. We keep going, and we get a natural expression for area. So obviously when x is 1/2, when x is 1/2, when x is 1/2, sine of pi divided by 2 is positive 1, and when x is equal to 3 on 2, sine of pi, 3 pi on 2 is equal to -1, so that's why the terminals change as they do. And of course the du dx, you've got the 1 on pi out the front there, and it was minus because it's negative signed area. Okay, so you look across to the options at this point, and you don't see that represented anywhere. -1, 1, -1, 1. So here's 1, but it's missing a pi. 1 on pi out the front, minus 1 on 1. It's not quite right, is it? It's close, but I'm looking for minus 1 on pi. Okay, so it leads you to think, okay, none of the options are there. Clearly this is just garbage because the change of terminals needed to occur. And so you're left with B or C. So you can see incorporating the negative. So incorporating this negative part, we could change the integrand, the function that we're integrating, or we could change the terminals either way and get there. And in fact, that was how we arrive at D. Okay, guys, you look at a question like that using a suitable substitution. You've got a complex function product with a linear function. So your thought should be going towards linear substitution. So setting u equals to the expression 2x minus a, the expression under the square root sign, expressing, there it is, letting u equals 2x minus a. Of course, you've got to think about du dx as well when you've got your change of variable. So dx is equal to half of du, and then of course you make x the subject of that relationship above, and wherever you see x in the rest of the integral, you replace it by u plus a on 2. The last thing, of course, is the terminals themselves. Upper bound of a, when x is equal to a, what is equal to u? 2 times a minus a is u is equal to a, and when a is 1, the lower bound is a on 2, 2 times a on 2 is a minus a is equal to 0. So that becomes the new terminals, u, 0 and a. In fact, so from there we can just eliminate a whole bunch of things not relevant. So we've eliminated 2 based on terminals. Let's keep going. And of course, making x replaced by a on 2, u plus a on 2, we can make that a single fraction and then take out the division by 2. So we've got 1/4. We're left with this is our expression, which of course simplifies to a minus u. It's all being multiplied by u to the half. And then you can see, what have we got? We've got C is the correct option. So when I expand that, so this is just the integrand, u to the half minus u to the 3 on 2, and with 1/4 the factor out the front. Okay, question 5, the shaded region. The region that you can see there is got boundaries y equals the square root of x over here, and so that's related to y equals the square root of x, and the part of the circle that I'm going to highlight in green that comes from this relationship. It's a circle of center 2, 0 and radius 2. All right, so that's the boundaries as well as the x-axis itself. So let's just highlight that. So this is the region that we're rotating about the x-axis. So, okay, you can see both of those regions are completely, it's not a difference of 2 curves that I'm rotating around a particular axis of rotation, because each of those regions is bounded by the axis of rotation itself. But what you're going to have to do is split up it into 2 separate integrals. So you're going to rotate the red function, the square root function, from 0 to 3. So that'd be volume 1 pi 0 to 3. And of course, that's integrating about the x-axis. So that's simply the square root of x all squared dx. And then, oh, by the way, how do I know it's 3? Of course, I had to do a quick little letting one rule equal the other. So wherever I saw y in the other rule, replace it by the square root of x, and it's a pretty easy equation to solve. X equals 0 or x equals 3. And then the second volume is, which I should do in green, pi, and you're integrating from 3 to 4. And in fact, if you make y squared the subject, it's pretty simply 4 minus x minus 2 squared, and I even left it in that form for you, so it was nice and straightforward. So option D was the answer. Okay, question 7. I had to give you one of these. They're pretty routine, so it's good to practice them. Okay, so let's have a look at our options. Functions of x and y. You've got a function of x and a function of y. Okay, so if it was just a function of x, then it would be uniform vertically if it was a function of x. So it can't be option B. And if it was just a function of y, it'd be uniform vertically. So you can see, take any vertical line, it's far from uniform, so it's not going to be a function of y either. So what we're doing is looking at a function of x or y. Okay, let's try to spot where it's dy dx is 0. So you're looking at these lines through here, dy dx is equal to 0. And if you just draw a straight line through those, where dy dx is equal to 0, it's approximately y equals minus x, or in other words, x plus y equals 0. So we're looking for that as a driver of dy dx is equal to 0. So we're looking for an x plus y as appearing in the numerator of the function. So it could be A, could be E, but it's certainly not option C. Okay, so now we go to our denominator part of the function. So let's just highlight that. Maybe I'll get orange. So this is where my eye goes to. So what I'm doing is looking for where is it that our line segments are perfectly vertical. So of course in this case this would be along the line y equals 1/2 x, and that would be perfectly vertical along the lines y equals 2x. Now that's why a scale was given to you to help you. So if you can see perfectly vertical along in this section, that'd be great. But you can see here's your vertical lines, not too many to actually grab hold of. Vertical lines. So that's a line with less a gradient than y equals x, and that's approximately y equals 1/2 x. So indicating A is your best bet. So that's the way to deduce the correct answer given the 5 options presented. Okay, question 8 was a classic mixing problem. A container initially holds 200 liters of water. There it is there, of which 100 grams of salt is dissolved. So there's our amount of substance initially, x naught. So a solution contains 0.1 grams of salt per liter. 0.1 grams of salt per liter. So that's a concentration thing. dx dv is all about concentration. That's 0.1 grams per liter. That's what's flowing in. Okay, and the rate of flow is 6 liters per minute. That's a dv dt information. So there's dv dt, and that's 6 liters per minute. Together, it gives us our dx dt information, doesn't it? So dx dt in ends up being 0.6 grams per minute. Okay. Now, what about how's it being drained? It's being mixed constantly, of course. Mixed constantly. That phrase will always be there. And drained at 8 liters per minute. So it came in at 6 liters per minute. It's leaving at 8 liters per minute. So every minute that passes, we're losing 2 liters. All right, that's important in our understanding. All right, so here's our dv dt out. Here's our concentration. Our concentration is always x, the variable matching the amount of substance in the tank at any time t. It's a variable amount, and here lies the beauty of the problem. So it's quite simply stated over the volume. And that's our expression for volume. Volume's changing as a function of time because every minute that passes, it's losing 2 liters. So when I multiply those together, I get a simplified expression of 4x over 100 minus t. And so at the end of the day, it's 0.6 or 3/5 minus that expression. And it turned out to be C as your answer. All right, this bit of information concerns questions 9 and 10. A mass M of fast-growing organism increases at a rate proportional to M at any time T years. Under certain conditions, the lighter the organism is, the more it is affected by an agent of decay. So there's the proportionality element that leads to increased rate of change. There's the element of decay. And so you can see the smaller m is, the greater that impact will be. All right, question 9. The organism will neither increase nor decrease, will remain constant, in other words, if under the above mentioned conditions, if its mass is what? So if it's not increasing, dm/dt is not positive. If it's not decreasing, dm/dt is not negative. What are we talking about? We're talking about when is dm/dt equal to 0. So what we're doing is just setting that expression equal to 0 and solving for m, and that's what's happening over there. And when I do so, it turns out to be 1/4 of a gram or 0.25 grams. By the way, that's probably a handy thing to file away. Constant when it's reached a terminal velocity or a constant state where things are not changing. Understand whatever your differential equation you're dealing with, it's arrived at a state where it's equal to 0. Okay, here's the final question of our multiple choice, and it's a case where the substance is currently 0.36 grams, and what we need to do is work out the number of years it'll take until it reaches 0.81 grams. So what we're going to do is set t equals 0 and match it with m equals 0.36, and what we need to do is work out the time it takes for m to reach 0.81. So here's our dE, and we need to obviously solve it. And how do we solve it? If it's a function of the dependent variable, we need to reciprocate it. But before you reciprocate, this needs to be a single algebraic fraction. Algebraic fraction, very important. Many students forget that. So I need to make that a single fraction, as I'm doing over here, and then reciprocate. Once you reciprocate, you can see your denominator. Okay. Well, you can see from the hints in the actual options, it's going to be solvable by method of substitution. When you do differentiate it, you've got 12 the square root of m, which of course is a multiple of the numerator part of my dE. So very solvable by method of substitution and change of variable. So what is it? It's going to be, here it is. Here's my expression for the denominator u, and it's du dm, but 1/6 of it gives me my numerator. There it is, and I've changed the variable solving for t, but what I'm after is a particular value of t for a particular value of m. So in this change of variable, I need to change my terminals. So so when m is equal to 0.36, our corresponding u, so let's see where that's coming from. Here's our u expression. So when m is 0.36, u is equal to 0.728. Is equal to 0.728. And when m is equal to 0.81, u is equal to 4.832, and then they become our terminals there. You probably didn't even need to bother to check because you know, you had limited options, and you could have under time pressure realized it had to be option E, given that the factor at the front was equal to 1/6. So, but that's the entire thinking behind the question and why the answer is as it is. So hopefully you did okay on your multiple choice. All right, question 1 should have been a pretty routine confidence building type of a question. Nothing tricky. We looked at several of these type of questions in class, and it's just Newton's second law. So what we've got is an article, a super duper in this particular case, might be the middle of summer. It's initially 18 degrees. We pop it in a freezer with a constant temperature of -45, and after 32 minutes it's down to 9 degrees. Let capital T be the temperature of the super duper in degrees Celsius, and lowercase t the time in minutes that the super duper remains in the fridge. How is it possible that that differential equation is determined? I was looking for a couple of key bits of information. Firstly, a reference to Newton's law of cooling. Okay, so Newton's law of cooling says the rate of change of temperature of the super duper will be proportional to the difference in temperature between it and the surrounding temperature. So temperature, so dt, dt, capital T, d lowercase t will be proportional to the difference in temperature between it and the surrounding or ambient temperature, which is negative 45, which of course comes down to T plus 45. Now we know it's a cooling, it's a rate of change that's negative. So when you convert that to an actual differential equation, that becomes equals to minus K constant of proportionality, always positive, T plus 45, and then that's where it's all coming from. So there's a model answer that you might have gone for. I was a little bit lenient here, but I was looking for Newton's law of cooling, or the understanding expressed above that dt is proportional to the difference between capital T and negative 45. Okay, so we're told that it will freeze when it hits 0 degrees Celsius. Determine how long it needs to be in the freezer before it reaches that point of freezing, and give your answer correct to the nearest minute. All right, now this question was done pretty well. Okay, so we've got our differential equation that we know we have to reciprocate to begin the solution process. Here's our initial condition information over here that will enable us to solve the constant of anti-differentiation. And here is further information that will enable us to determine the value of our K, the constant of proportionality. So let's begin the process. We reciprocate, as we said, we anti-derive. Now, a lot of you actually put mod in your expression over here. There was no need to put in a mod. Why not? Because capital T plus 45 must be greater than 0 for all T. It can't, the super duper can never get colder than minus 45 and will approach it. And so it's okay for all T. So it's okay to just drop the mod in those cases. It's drop the mod where you can, but you need to justify or have a good reason for doing so. In this particular case, capital T plus 45 could never be 0 or negative. Okay. All right. So that's a nice little tip for some of you out there. All right, so when T equals 0, okay, so we've done that. We're applying our initial conditions as we said above. When T equals 0, the temperature is 18. So we can get in our expression for C, our constant of anti-diff. And then we've got our T expression now. It's getting closer to something known and precise. But we still need to work out our constant of anti-diff, and we do that by applying this additional information. Temperature reaches 9 when 32 minutes is reached, enabling me to come up with this expression for K. So multiplying by K, dividing through by T, and of course 9 is a common factor in 63 and 54, so it simplifies to this. So I have my K factor as well. I keep going, okay, and therefore I replace K with natural log 7 on 6 divided by 32, which gets me a generalized expression for time as a function of temperature. Now, a lot of you just blindly, in fact, perhaps going to tutoring schools or whatever the case may be, you're working with other methods of which leads you into expressing temperature as a function of time. That's all well and good if the question required you to get temperature as a function of time. But in this particular case, question B, it's more helpful to have time as a function of temperature, because what we need to do is work out the time for a particular temperature, and that's what we're going to do from here on in. We're going to replace temperature with 0. We're going to get an expression for time, and then I could have in fact got you to work out the time as an exact answer, but of course it's not as meaningful as an approximated one. Turns out to be 69.8, which is approximates to 70 minutes. So this was done quite well, but just my tip for you guys out there, if no need to use a mod if what's being applied to the mod to the argument of the log is always going to be positive. Okay, this question was also done reasonably well. We have to, rather than have the relationship in terms of time as a function of temperature, we need to reverse that, have temperature as a function of time, which is absolutely the more natural way to read the relationship between the two. Okay, so what are we doing here? We're taking this multiple of our log and dividing it by both sides to create this expression on the other side of the equation. What are we going to do then? By the way, this was done in so many different ways. This is just one approach you can do. We're going to make the argument of the log expression the subject of the equation by converting it to an exponential relationship. So it's the exponential of the natural exponential of that expression on above. Okay. Now, of course, what I can do is plug it, take that t divided by 32 and make it a power inside the natural log function. And of course, if I've got e natural log of some function of t, it reduces to that function of t. So of course, this entire expression then becomes the result, 7 on 6 t to the 32, 7 on 6 to the power of t on 32. So here we are, 63 divided by temperature plus 45 is equal to 7 on 6 to the power of time divided by 32. And then it's just a case of making capital T the subject, multiplying across, dividing by 7 on 6 t to the power of 32, making it minus 7 on 6, 63 times 7 on 6 to the power of minus t on 32, subtracting 45, and there we are, we end up where we needed to be. So that's not the only approach to this question. Some of you unpacked it in a different order, in a different manner, provided it was mathematically sound, I was happy with it. Okay, part D, the sketch. So I was looking for an exponential shape. Some of you just whacked this into your CAS and drew exactly what appeared on your screens without actually thinking about what sort of function you're dealing with. It had to look curved like an exponential graph, and of course it needed to have that asymptote, so it approaches negative 45, the ambient temperature, the temperature in the freezer itself. Now what was nice was this was given information, started at 18 degrees, and it took 70 minutes to get to 0. So we actually had the intercept information at our fingertips from either given information or from part B. Now, it's fair enough of you to question. I've actually used the approximated value for the x-intercept. It doesn't state that I should, so a lot of you had the exact form of the x-intercept, which was whatever it was, some multiple of log, natural log divided by natural log. That was probably a more judicious, conscientious approach to working out the x-intercept. Others of you had 69.8 with several decimal points. It should have been stated. I accepted anything accurate to the question. So, but no, it should, if it's not stated otherwise, you should probably label it as your exact value, which many of you did, and I was pleased to see that. So, yeah, but I accepted any approximated value for the x-intercept in this case. Okay, and on to the final question of part 2 of SAC2. So what we have here is a curve given by the rule as follows. It has the rule 16 divided by the square root of x minus 2 minus 4 from 2 1/4 to 18, and even displayed for you on the set of axes. You didn't need to have to graph it. And even better than that, I've given you your x coordinates and your y coordinates, which is particularly helpful. Is what you're doing is creating a carafe, a vessel that holds liquid, and I'm doing it by taking that shape and spinning it around the y-axis. So what you're going to do is focus on the y components of those endpoints and then of course take your function and make x as a function of y. So which you can do all quite nicely with your CAS. All right, so when you do, so of course, what would you enter in your CAS? You'd go solve, so you'd define f of x above, and then you just solve f of y equals x for y, and then you get your rule for your inverse function that you see over here. Then it's a case of pulling out your rule for the volumes of solid of revolution. Don't forget your pi out the front. Upper bound 28, lower bound 0, taking the rule and squaring it, integrating with respect to y, and you get 2,125.8 mils, 0.81 mils, correct to 2 decimal places. So that was done pretty well, and taking careful note of the question, you're asked to take exactly 2,125 mils as the true capacity of the carafe. So hopefully that did one of two things. If you got that as your answer, you felt supported and encouraged that you're on the right track. And even if you didn't, you could just take that value and run with it thereafter. Okay, H is the depth of wine in the carafe as measured from the center, okay, in centimeters. V is the volume of the wine in the carafe in mils. Show that V as a function of H can be written in this particular manner. Now it's a 1-mark question, so I was only after one piece of information really. And really what it was is the same working out as you had above, but rather than integrating from 0 to 28 to work out the total volume of the carafe, you'd have H as the upper bound in that integral expression, and that was enough. You could have, if you threw that into your CAS, you could have verified that that is in fact the expression that results. Now, some of you actually integrated, just did an indefinite integral, and then used the fact that when H is 0, when the volume is equal to 0, when H is equal to 0, and came up with a constant of anti-diff. That overcomplicates things when simply you could replace the upper bound, the upper terminal, with this variable H, and it captures the volume as a function of H really quite nicely. All right, moving on. If a bottle of wine is 750 mils and 2 bottles are emptied into the carafe, we've got 1500 mils in the carafe. Find the depth of wine in the carafe as measured from the center. So find the value of H when V is equal to 1500. This should have been a real no-brainer. Yeah, so take the rule as given to you or as established, either one. So that rule as mentioned above, and set V equals 1500, solve for H, let your calculator do the work, and you get your H value from there. That really shouldn't have been too difficult. In fact, it was pretty generous even to give it 2 marks, 1 for method and 1 for the final answer. Okay, part D was not done all that well, actually. Some people got partial marks. Those of you who recognized that this was a related rates question were made at least partial marks, but it wasn't done as well as what I would have liked. So what we have in this situation is wine is being poured into the carafe at a constant rate. So every 8 seconds that passes, 1 litre enters. So in other words, the rate of flow is 1/8 of a litre per second. Now, what we need to do is find the rate at which the depth is increasing. So find dH dt when H is equal to 10. So that's what we need to find. That's our objective. So we're given this. We need to find dH dt. What's the missing link? Is a link between volume and depth, which we've actually established previously in the question. Now, before you progress any further, I wouldn't leave dV dt, the rate of the volume of water entering the carafe, as 1/8 of a litre per second, because what's important in a related rates is the units must be consistent. So litres don't match nicely with centimetres, and take note of the question. dH dt must be in terms of centimetres per second. So what does align with centimetres in terms of volume? So centimeters cubed. Each centimeter cubed is equivalent to a mil. There's 1,000 mils in a litre, so what you needed to do is take that 1/8 of a litre per second, multiplied it by 1,000, and what you got was 125 mils or centimeters cubed per second. It's now in a compatible unit form to the other information, the information we need to link where we find dH/dt as centimeters per second, h as a function is in terms of centimeters, and time in seconds, of course. So that's all nicely matched up. All right, so once we're aware of those adjustments that we need to make, we pull out the old chain rule. dH/dt is what we need to find. dV/dt is given, so we need an expression for dH/dV. So we go back to our volume expression given to us above, should be in our CAS calculators already, and we differentiate it with respect to h, and we arrive at this ungodly expression. But that's all right, we can make our lives much easier by just whacking h equals 10 immediately into it. So we get a much neater, more compact expression that we can work with by replacing h with 10. Okay, we need to obviously reciprocate that. Sorry, that's already done. So that's dV/dH. So we replaced h with 10 and reciprocated to get a dH/dV expression. And so what we're doing is taking 125 centimeters cubed per second and multiplying it with this information of centimeters per centimeters cubed, and then we whack it into our CAS under approximate values under decimal on a decimal settings and get 3.64 centimeters per second as our answer. All right, let's continue. The problem takes an interesting turn. Apparently the wine carafe is used at a valedictory party, and the mood of the party, people are getting maybe a little too intoxicated, let's say, and so a decision was made to dilute the 1,500 mils of wine currently in the carafe with pure water. Okay, now that pure water is entering at a constant rate of 150 mils per second. That's the rate of entry. Okay, now the wine, in fact the carafe, it should be said just the contents of the carafe, is stirred constantly. Now, when you see that expression, you know where you're going. It's a mixing rate problem. That's what's coming further down the track. And it's drained, the contents are drained, it's leaving at a rate of 125 mils per second. All right, now the first question is just to put it into a practical context. We can see 150 mils per second is entering, 125 mils per second is leaving. What we have is a net gain of 25 mils every second that passes in this dilution process. So what's the available capacity left in the tank? Well, it's the capacity of the tank left, the difference between that and the amount of wine at the beginning of the process. So it's obviously 625 mils left to fill in the carafe. If we divide it by 25, we'll get the number of seconds. 625 divided by 25 is 25 seconds. So that's how long it'll take before, in fact, if we continued on with the dilution process, it would start to overflow. All right, now, as I said, the clues were in the text that where we're headed is a mixing problem, and that's what you had to do in the next part. Only worth 1 mark, but setting up the DE was simply applying the model for setting up differential equations in mixing problems. So W is the amount of wine in the carafe in mils, T seconds after the dilution process. Show that the rate of change of W with respect to time can be given by that expression. Okay, where is that coming from? It's pure water. Don't forget, pure water that enters the tank. So the concentration of W with respect to volume coming in is 0 cubic centimeters per cubic centimeter. Now the rate of flow coming in, we're told, is 150 centimeters cubed per second. When I multiply the two via the chain rule, what do I get? I get a rate of change of W with respect to time coming in, and that will be equal to 0 times 150. It'll be equal to 0 centimeters cubed per second. Okay, there it is there. So dw dt in is 0, dw dt out is what? It's the dv dt out, so the rate of flow out, which is 125 mils or cubic centimeters per second, times by the concentration. All right, where is that coming from? W is that variable representing amount of wine in the carafe, constantly changing as a function of time. What about that denominator? It starts at 1500, and every second that passes, we gain 25. So that's where that's coming from. So putting that all together and simplifying, we come up with the required expression for the DE. Okay, part G was just simply solve that. Even if you had no idea where dw dt expression came from, you had to solve it. And of course, what was I looking for? Separation of variables again. So when you do separate the variables, you've got those two integrals on either side of the expression. Quite a simple transition. Now we know both W and 60 plus T are both positive, so there's no need to invoke the mod. We can drop the mod and just go for a log of the those particular arguments without the mod. Okay, plus C, our constant of antidiff. How do we evaluate C? Of course, we've got our initial conditions. At time is 0. There's nothing but wine, so we've got 1500 mils of wine, so W is equal to 1500, and then we can get an expression for C from there. Okay, I could clean that up and make it a single log expression, but I won't. I'll keep going. So I put it all together. Okay, there it is. So minus 1/5 natural log W equals natural log 60 plus D. So because I want to make W the subject of the equation, just multiply everything by -5. So that's what we're going to do here. Take every term and multiply it by -5. And we get quite a nice neat expression. And now at this point, what I'm going to do is make that single log expression and then just marry up the two arguments. So we've got, here I'll just get a different color. We're going to reverse plog, power of -5. We're going to combine these together. Sorry, we're going to reverse plug as well. 60 to the power of 5 times by 1500 becomes the numerator, and 60 plus t to the power of 5 becomes the denominator. So log W is equal to log of this expression. We can equate logs and come up with this expression for W. And sorry about that numerator being so vastly big, but that's why I was encouraging you to leave your form of the answer as a product of expressible powers. Whacking it into the calculator, it turned out to be something very large indeed, something of that order of magnitude. Okay, so that's how you solved W as a function of T using separation of variables. Okay, we're on the home stretch. How much wine is in the carafe after 6 seconds? Well, clearly, if you got the correct answer to the previous part, it's just simply whacking in 6 for T in the expression and coming up with your answer. Look, if you had the incorrect answer but substitute 6 for T and got something reasonable, an unreasonable expression, of course, would be where the wine value was greater than 1500 or very, very close to 0 or negative. Provided you had a reasonable answer, substituting 6 for T in your expression for W as a function of T gave you an H mark. So it really isn't, I mark this as a his/her mark, a consequential mark in the most part. Not always, but in the most part. Okay. All right, so this is where people sort of fell off the cliff a little bit. You have to think a little bit about what you're doing. Okay, if the outflow of increasingly diluted wine is used to fill empty bottles, each with a capacity of 750 ml, find the concentration of wine in the first bottle collected. Okay, now here it is. So we know after 6 seconds, so every second that passes, 125 mils is being drained, and after 6 seconds, a total of 750 mils is drained. So Hence, we get the contents of the first bottle after 6 seconds. So after 6 seconds, we know there's 931.4 mils left in the carafe. If we started with 1500 mils in the carafe, it means that the amount of wine that I've collected in the first bottle of 750 mils is 568.6 mils. Okay, so if that's the amount of wine in mils out of a total bottle of 750 mils, it's easy to convert that to a percentage, as you can see on the right, and it turns out to be 76%. So proportion out of the whole times by 100 gives you the percentage concentration. And finally, the last part of the question, you had to think a little bit about this one. So maybe you haven't seen anything quite like this before. How long does it take after the dilution process begins to reach a concentration of 40% wine in the carafe? So we're not talking about bottles collected anymore. We're talking about 40% wine left in the carafe. So this is where you had to go back to your expression for concentration. The concentration of dW/dV outflow is the same as the concentration of wine in the tank at any time t. Why? There's the constant stirring. It's constantly stirred, so the concentration is uniform throughout. That's the thinking behind it. So concentration outflow is equal to concentration in the tank at any one point. So what we're interested in is, when is the concentration equal to 40% or 0.4? Now we can't solve that on our own, so what can we do? We can bring in our expression for W as a function of T, and we can solve simultaneously. So here's one equation, here's our second equation. When we ask Kaz to solve simultaneously, we get a pair of values, and of course I'm only interested in the T value, and that tells me the time it takes for the concentration of wine in the carafe to reach exactly 40%, 9.90 seconds. So that's the end of the paper. It was done better than expected, I have to say. And I think it's looking rosy for some of you, and for others, there's quite a bit of work ahead of you. So goodbye for now from me, and see you soon.